Thank you, Josh. Like you say, I know Josh now for 12 years. It's the first time I'm in Kingston. I was following the evolution of the Ingenuity labs through social media, so I'm very happy to be here today to see where they are at. I got a very nice sunrise by the lake this morning, so up to now, Kingston looks very great. So today, my talk will stay rather general, given the crowd. We'll talk about field robotics. So field robotics is testing robotics solution out into the wild, close to the end application, and see if we can gather some research questions and go back to the lab and solve them. So through the talk, we'll see how we managed to raise a couple of million through the DARPA Sub-T challenge for the teams. While our researcher was doing the first 20 autonomous driving kilometers in a remote forest. So the take-home message here is that although field deployment costs a lot of money, when done well, it can actually bring back a lot of funding through a lab, so then you can go back and continue to have fun with the robots, essentially. Like just say, I'm the head of the NORLab, the Northern Robotics Laboratory. I started 7 years ago with only me in my office. Now we are getting close to 30 researchers in the lab, highly focused on PhDs. Today's talk is actually the sum of all of their work, so I want to acknowledge them as they do most of the research up to now. At NORLab, we have 3 major trusts for research. So we do autonomous driving in snow conditions, where we had our research program Snow and Cryotic. We also have a trust in AI for forestry, and everything related to search and rescue activities on the ground or in extreme environment. Today's talk will focus on subarctic environment and on subterranean. Although we have a great dedicated team to AI in forestry, so just to quickly touch, this is the kind of work that we are pulling off in that area. So forestry didn't saw much of innovation lately, so we tried to move to precision forestry in that area. We were lucky, one of our working on segmenting timber was actually picked up by Segment Anything from Meta as their benchmark, and as of last week for Segment Anything 2. So we are actually happy for that, but that won't be the focus of that talk today. How many of you know what is DARPA? Not too bad, so close to half. DARPA is the US Defense Agency related to research. They tend to be 20 to 40 years ahead. Although there's defense in their word, they usually tackle general challenges. So they are upfront for example, the Moderna vaccine, weather satellite, GPS, personal computer back in the days, and even internet, they were funding the basic research at that stage. So although there's the word defense in there, they are funding usually high risky research in general. So around 2004, instead of doing the classical NSERC proposal where they open a contest, you apply, receive money, and do the research, they flipped that to challenges, especially for robotics. So teams would participate to the challenge, and they would give money only to the top 3 participants. So this is how they kickstart all of the autonomous driving section that we know right now. So in 2004, there was a race in the desert. In 2007, there was an urban challenge in a city. And this is where you had all of those autonomous driving companies that started from there. In 2013 to 2015, they went into the humanoid. And actually, we started to know a little company called Boston Dynamics that is now all over social media. So they got seed funding to build the Atlas robot at that time. And then now we see the whole influence of humanoid robots that moved to the industry. So DARPA had quite some major influence in the robotic environment. And their latest challenge was the subterranean challenge, where we could participate, which is exactly at the time I started as a professor. So it was a bit sketch at the time, but we managed to relatively do well. It costs a lot to organize those kind of challenges, so they invested up to $82 million for that kind of event, and the top teams would win $4 million if you manage to win this challenge. By the time the registration of the team started from only US teams up to more and more international participants. So for the sub-T, we had people from Australia, Zurich, and for the first time, we had the Canadian participants. So in 20 years of existence, we were the only team to manage to qualify and also to win some couple of positions in the challenge. We were up to, for example, a team that was with GPL, so NASA, MIT, CCECE, so the top university in South Carolina. All of those universities were in the same team called Co-Stars. So that's the kind of level that we're dealing here. It's not a student contest. So it's all of the best labs in robotics that try to tackle a difficult problem. What was the problem? So they wanted us to move into 3 different types of underground environments. So main tunnels, mostly related to mines, for example. Urban or underground environment, everybody was expecting a subway station, for example, to investigate, but we had the decommissioned nuclear plant. COVID happened, so the natural cave challenge were canceled, and the final, we were promised a place where all of those environments would mix up at the same, in the same location, which confused all of the team, and we were wondering how they would pull that off. We finished it in Kentucky, where there is the mega cavern, and they actually hired a movie set team to build all of those environments within a large cave. So we can see that would be the natural large environment. So this is a 3D map of the area. So that would be the typical size of the room, and all of the other places were made as a movie set. So we have an old school mining area on the top and sort of a natural cave. And all of that was there to challenge the type of 3D reconstruction that we need to do. What we had to do to win, we deployed a fleet of robots that had to find artifacts in a search and rescue mission. So artifacts could be a helmet, a backpack, a cell phone, a survivor, a rope. For example, we'll get the list up front. And then the more the team of robots could explore, the more points you could get. You need to report the artifact within a bubble of 5 meters. So you had to localize to be able to win a point. They went up to even build a full subway station with graffiti, posters, signs. All of that was actually in that area. So how does it look like? Our lab is specialized in 3D localization in mapping. So this is the kind of representation that we are usually doing. The white points that is moving around, that's actually the LiDAR. So that's the field of view of the robot. And the color point is the 3D map that we're building live. So in order to be autonomous with a system, you need to think that we have all of the computation power within the embedded system. So we need to be able to know where we are at, find the artifacts, and report that to the base. And of course, there's no communication, no high bandwidth. So we need to deploy our own setup within the mine. So that was our part. We teamed up with the Czech Republic Technical University, for which they had the larger interface. And this is the kind of computation that you need to pull out to autonomously navigate in underground environment. So here you can see the spot moving around. All of that is post-processed, of course, to make it nice and easy to view. But we need to localize 3D map, find traversability map at the control. And you will see the trigger for the helmet that is flashing right now. So we need to detect the artifacts and report that to the command post. So usually people will cut that part out of the video, but I need to say that the spot, although it has the capacity to raise, most of the time when it would fall in the small gravel, the motors would stay in segfold. So although the advertisement is that the spot is great, in our experiment, when we deployed outside, actually, most of them were actually on the ground after close to 20 minutes. It's not the only thing that we saw happening there. This is the CoStar, the GPL team, where they would use the drone as an antenna for communication, but actually none of the other robots would detect the drone as an obstacle. So what would happen is that the video will go on and go on. They would just smash the system over and over. There's another robot that is coming up that will just drive fully over it. So when we talk about field robotics, that's the kind of thing that happened, and all of the teams that would, here we go, it will go over. That's the kind of things that it's very hard to figure out in advance, but now we need to try and see what happened to perform better. I really enjoyed that video. So this is the CSRO team from Australia. You need to think about how hard it is to first be there, so I will explain. They autonomously explore something like 50 meters down the tunnels, discover this storage area, realize autonomously that that the roof is quite high. That robot was carrying a drone, so deploy the drone autonomously to detect artifacts from above, and this is what happened. So we are already at the stage where the drone managed to take off, and all of that effort was stopped right there. Again, that's the kind of thing that, although if you do the simulation, you will not simulate that part, and we need to try outside to build better and more robust system. I'm showing crashes of other teams that also have burned drones, and when you go to those competitions, you don't really expect to come back with your full system operational. So in terms of science, what we get out of that, after the competition, we could gather all of the top 6 teams and produce a survey of the top SLAM architecture that were used. So SLAM is for simultaneous localization and mapping. Something that we realized that all of the team aligned with tightly coupled LiDAR IMU solutions. So when IMU is the initial measurement units, none actually use vision for this kind of challenge. And within that survey, we pull out openly all of the dirty details. So it's a competition, so you patch eventually to make it work. So we make it open to the public, all the repo, the data set, and open some future direction for research. What we got out of that, after coming back, the National Defense asked us to do a technical demonstration for our capability. And this was our original system that we demonstrate. Now that we can do mapping, we can actually go somewhere and ask the robot to come back autonomously, and we're independent of the light condition. And what they ask us is to map radioactivity within the 3D map, so they have the no-go zone when they send the people. So that demo is scheduled for 2025. If we change from subterranean to subarctic environment, within the last 5 years, we worked on the SNOW program for self-driving navigation optimized for winter. It was a collaborative project with General Dynamics Land System. And at Quebec, at Laval University, we are very lucky to have a research forest that is close to an hour of drive up north. That research forest is about the size of the island of Montreal. There's no one there. We can fence the area, so we can take more risk with the autonomy of the system. The special trick of that place is that there's 6 meters of snow falling every year in that area, and we have 6 months of winter, essentially, up there. That's the southeast border of what would be considered as the subarctic forest, which is good for us to to push the boundary of where we can deploy autonomy. So, like I said at the beginning, we managed to do a resupply mission for a week. So we do back and forth between a garage and a remote cabin. And we check whether we could actually do it autonomously. So when we are talking about unstructured environment, this is what I'm talking about. Here, if you think that trees are static, this is how much it can bend when there's wind. So the drone, for example, is struggling to hold his position right now. Everything is moving. Snowbank will move with wind. There will be snow precipitation within the deployment. So we need to figure out solution to be robust to all of that, so that if in the future there is autonomous cars, they will need to handle those specific points. Winter is happening in Kingston as strongly as in Quebec. And most really, we doubt that they are robust to those conditions. So we're trying to find applications that are further away so that we can research those problems in a safe context. So again, we're specialized in 3D mapping. So this is the kind of representation that we were doing of the area. Since we are LiDAR-based, we can pass through the days and nights, and we were able to show that we were robust to snow precipitation, rain, and high wind, for example. So the study we had out of this, we'll not go too much into details, but we make the distinction between a road and a trail. So a road is rather large, and actually GPS signal can go through. The more you go narrow to the trail, the harder it is for the GPS signal. So we did a sensitivity analysis with the number of satellite needed to follow a track with the GPS, the GNSS. We were lucky to have a weather station that gave us reading at 10 minutes, so we could correlate the weather event with our autonomous driving algorithm. So as a quick view, any color bar is the type of precipitations that happen during our deployment. So we moved from rain to snow. There was actually a snowstorm during our deployment. And the curve that is going up and down is the temperature going under zero, so sub-zero, to up to plus 12. So we managed to show at least robustness from minus 12 to plus 12 degrees. Although it looks good, the actual range of doing multi-season in that area is that we need to cover minus 32 to plus 32, which involve a lot of water in the trail, a lot of challenges for navigation. And now that we know that, our next step is actually to pull out a multi-season data set where we would cover all of the well-defined seasons and all of the challenges that we cover. The last one was a stability analysis about the LiDAR localization. We also push a bit further in using the IMU and the gravity to limit drift. So if you're localizing in an odometry way, you will eventually drift. So any global cue that you can pick up, I'm talking about localizing here without GPS, is great. So we show how to do tightly coupled scan matching, so registration, using the gravity vector, which allow us to, on a 1.5 kilometer long map, reduce the drift, at least in Z, by 55 meters. Evaluating localization in those hard conditions is tough. Ground truth can be hard to gather. Like we show that GPS can have its limitation. Even if we do 3D mapping underground, there's clearly no GPS, so we had to build our own rig to pull out ground truth. So we are the first, as far as I can see, lab that can recover the 6 degrees of freedom of a vehicle, so the translation component and the two attitude component, by combining 3 theodolites, so 3 total stations. So now we can gather the ground truth trajectory in complex environment independently of GPS, for example, which is typically used to compare SLAM algorithm. We do also more and more control, realizing that the trickiest part is to be able to tune the tire and ground interaction. So usually when we deal with road, that will be fixed. You can tune it once, and then most probably the asphalt will be the same further down the road. when you're outside, we have patches of ice, there's deep snow, there's dirt, there will be saturated ground with water. And all of that is actually hard to predict what would be your motion, even within 5 to 6 seconds. So now we deploy, let's say, a standard way to evaluate those. And here's some sort of results that we produce. In green, for example, that would be the area that the manufacturer is telling you that the robot is able to operate. That's the turning rate and the linear velocity. In orange, that's actually what the wheels are able to produce at the encoder. And since we're able to localize in real time and relatively fast, we can even measure what the actual motion of the robot is doing. And that would be the bluish, purplish area in the middle. So now if you have a controller, instead of spending time in area where you can actually, the system is not able to do it, we can actually have more clever controller. The conclusion of that is that we can stay in the kinematic zone. It's not too bad actually to do it. So now we are moving it to the more dynamic system where we try to see what happens when we need to more complicated area where the inertia of the system actually make it push around. So that was our program for the last 5 years, out of which I'm happy to say that we'll launch the Robotiq program, which is $6 million for the next 5 years, again, sponsored by General Dynamics, on which we added Hydro-Québec and the RDC, so the Canadian Defense Research and Development. So the current state of the art to inspect the power line in Quebec. So in Quebec, the power is coming from dam, and the dam are up north. And so you have those huge power lines that move down north up to Montreal or all of the city. And they tend to carry snowmobile under the line, and then would drop them, and then they would drive and have a visual inspection of what is happening. So of course we're asked if we could help, or at least foreseen a future where that could be automatized. Here's a figure pulled out from the research proposal. So there's a bunch of work. Can just focus on the yellow lines, which are the path and the tree area where we'll focus our research. We'll continue the resupply kind of mission. So this is what we did within the other program, where actually time is critical and carrying the goods is relatively more important than the environment. So we can actually push through the environment and modify it, let's say, to make sure that we arrive on time. And that is opposed to the inspection of electrical substation. So when you have those big electric wires, you need to pass through substation that will lower the voltage up to the 120 that you get in a city. And they relatively look like that, and they are up north in Quebec, so it's complicated to inspect them, and especially complicated when there's a snowstorm, freezing rain, and all of that. This is where you want to have a system that can actually monitor what is going on. And as opposed to the other application, you don't want the system to touch anything. So at the provincial level or even the federal level, anything related to electrical is critical infrastructure. So here you don't want to push. You want to stop or to come back to charge for the station. And in between, we have a nice playground for deep snow autonomous navigation, for which there's clearly no literature up to now, so very few people research that. And the goal is to send a platform that would monitor the power line, and we are not in reusing data anymore, so here we can reuse the information of the past path. Here, the goal of the platform is just to go as far as it can, and eventually an operator will pick it back and change the battery and continue. So within the same program, we're touching different kind of autonomy, always in the extreme type of environment. And here are just a quick early test that we did to motivate the funding. So when I was starting into pushing robotics into the north, we did a survey of all of the deployment that happen in the cryosphere. So the cryosphere is all of the area on the Earth where water can be found solid, to realize that there was actually not that many that were deployed in all of those environments. So we identify, I think there's 6 or 9 biomes, and most of them were done late in the early days with GPL and NASA investigation. A couple of Canadian researchers, so the Robotics was deployed by the University of Toronto on Devon Island. We started with the Warthog on the frozen ground area, and lately we had the opportunity with the Hills program to go to a glacier in Alberta. So the Hill program is actually a program by GPL NASA, where they envision, so always very far in the future, to have a snake-like robots that will go into one of the moon of Saturn, go down one of those vents, where there should be ocean under and detect life. That's far-fetched and far in the future. What we were asked to try is see if we can provide the 3D localization system for such a system, and answer the question, what would happen if the robot would drop a bit and have some hard trajectory or hard motion going down. So we went to their field deployment so that was last autumn, in Alberta on the Arthabaska Glacier. If you know, glacier is actually quite harsh environment. Within 30 minutes, it will rain, wind. You have your laptop, you're trying to deal with it and to record some information. And what we propose as an experiment, nowadays LiDARs are getting cheaper and cheaper, which was the setup for that experiment. So we build a rig with a LiDAR, an IMU, an onboard computer, relatively well protected within a cage, and we literally throw it down the glacier and down the path and see if we can actually map the whole area. Turns out that we could. So that's a map of, I think, 38 meters done in 8 seconds of tumbling, which is relatively fast. So this is what we would call extreme trajectories. And here's the map of the moulin. So the moulin is on the glaciers, the natural cave that will be built when there's melting water that will funnel to a place and then build those ice caves. They are relatively dangerous, so people don't want to go down there because there will be a river that flow under them. And we could show that within few seconds, we can actually scout the environment. All of that didn't come out of nowhere. We had actually a practice round in our laboratory where we spotted some nice research problems that when you start tumbling at that speed, so the IMU is measuring linear acceleration and rotational velocity. The IMU can actually saturate. So you see the blue line, that's actually the signal for the, let's say, regular IMU that we use. We put a fancier one to get the ground truth. And if you are in those situations where all of the solutions now do tightly coupled LiDAR and IMU algorithm for 3D localization, of course, your map will be messed up. And our latest research, we could show that we can reconstruct the signal, the missing signal, using the linear acceleration and some free fall assumptions. So our maps pass through those saturation now, and we can go even more extreme motion for 3D mapping. Where are we going with that? Because we got the review that this is not robotics, you're just drawing sensor into a pit. This autumn, we have this 1/5 model that will integrate with LiDARs, and then now we'll start to be able to do some jumps and to see. The whole point is that the software shouldn't break. The platform should break before the localization, so that's the goal I'm giving to my teams. So we'll equip that with a LiDAR and IMU and continue our research. And down the way, to connect that to the research proposal for Robotiq, we figured out that there's a company building those very nice robots, essentially, that are only the track of a snowmobile, and we'll start to do some also extreme trajectory in snow. Here, of course, it's an expert snowmobile driver, but that's the inspiration for the students in the lab, let's say. We were also lucky in terms of opening. So our safety officer was Christian. He's an official National Geographic explorer. When he saw that we could actually scout the area within a couple of seconds, we started to brainstorm the idea of a small backpack with a tether and something that you can throw. So usually they would explore. So here's going down one of the, I think the only active volcano in Canada, which is building that cave, but it's super hard to see where you are at. He told us that most of the time when he's doing exploration, he have a map and a pen and paper. So we are looking forward to have some sort of a backpack that he could carry, and then instead of gearing up to go down, he would just throw the sensor and see if it's worth its security to go down and continue to explore. So that's a nice opening that we have there. All right, in terms of high-level conclusion. So for the type of robotics that we are doing, data is rare, and data is actually very costly to gather, which in an area where most of the students now do simulation and data sets, that doesn't help us a lot. So here's my strategy for the lab to actually move beyond those limitations and being able to push research. So any new system that we receive, I ask the student to get out with it as soon as we unbox it and do some manual driving and try to push the limit and see what the system can do and be with the robot to understand these physics, for example, although they are in computer science or in other area. Once you do that, you can have your early data collection based on manual driving. And then you can start with your simplest model ever. The only thing is to make the robot move by itself. And once you're there, once in a while, you pick up already a challenge. In the case of the cube that we throw, was clearly manual driving just by throwing it down. But we saw the saturation of the IMU, and this is how we started the research out of it. Once you're there, this is where it started to be interesting to move to the other step and have some adaptive models, which brings some assisted solution for driving so people can have it more and more, which bring even more data. And at that point, you can start thinking about machine learning, autonomous driving, and larger data collection and augmentation. And within data augmentation, I put simulator here. So this is where I'm sitting in terms of strategy, and my goal is there's once in a while students that want to try already machine learning algorithm without knowing anything about the system. When it doesn't work, the student cannot tell you why, because he doesn't understand the platform, doesn't understand actually the problem behind, which make it relatively complicated. And this is where I see the value of field robotics, and this is the whole expertise of the lab. So my job is to make sure that we consolidate algorithm and that I find funding for infrastructures and to motivate the students to go outside and play the robot as much as they can. I will use my keynote position for some advertisement. Quickly, we're looking for a postdoc that would like to boost his research portfolio. If some of those activities interest you, please talk to me. More importantly, or in general, I'm also co-chair of the F110 competition. We have an undergrad club in the lab that we are supervising. They are twice world champion for that competition. If you are students, that's a great place to start with field and system that move. Most of the time, here it's nice, but that's when it's working. Most of the time, your system will go crash to the wall. And if you just want to know how is it, we are organizing one competition in Niagara Falls in September, and it's free to attend. So if you just want to show up and see what is the actual competition, please come. If there's no team at Queen's, I would really like to have one team in most of the universities. So instead of the student showing up in Japan for a competition, we could have a regional competition and boost the level of all of the area. So if you're a prof, it's actually super fun to watch the racing car spinning and going to the wall most of the time. Final advertising, I'm the funding member and co-chair of the Canadian Robotic Council. So if you do anything related to robotics and you're not registered yet, please register. So this is not just a research activity. We actually try to unite the stakeholder, and we want to catalyze robotics in Canada. So we have some sort of productivity issue in general, and we have little transfer into the industry in terms of robotics activity. So please have a look to the website, and if you're doing any of those activities, register. It helps us to map the environment and consolidate Canada. Canada is large, and it's actually hard to know what is going on through the whole country. Here's our collaboration. The last statement is that we are having startups now out of the lab, and that's also helped to keep the whole ecosystem of robotics working. You can follow us on LinkedIn, YouTube. All of our code, even though we tend to be on the defense side, all of our code is open source. That's my job, to let it open as long as I can. And up to now, even the next program, all of the code that will be produced will be open. On that, I'm a bit early. I will take some questions and let you with some manual driving experiments for the students.